Good morning, all of you. Today we are going to discuss about the scalar and the vector magnetic potentials. Scalar magnetic potential is represented with the V suffix m, and the units are going to be amperes. The vector magnetic potential is represented with the A, and the units are going to be Webers per meter. When we discuss about the magnetic field, we have seen that there are a number of similarities between electric and magnetic fields. For example, electric field intensity E, the magnetic field intensity H, both are analogous. Similarly, electric flux psi, the magnetic flux phi. Similarly, there is analogy between electric flux density D and the magnetic flux density B, epsilon and mu. The Gauss law, which is defined with respect to electric field, is analogous to that of Ampere's work law in the case of magnetic field. Similarly, you observe a similarity between the Coulomb's force law and the Biot-Savart law. In both the cases, the field is inversely proportional to square of the distance. Like that, when we discuss about the magnetic field, we are going to observe that there are a number of similarities between electric and magnetic fields. Now, in the case of electric field, the potential function has played an important role. It is related to electric field intensity with this equation. E is equal to minus of grad V. Basically, V is a scalar quantity, so it is more easy to work out in terms of the potential function, which is a scalar quantity. See, it is something like, suppose there are 10-point charges, Q1 to, let us say this is Q10. At a given point P, you are required to find out what is the total electric field intensity. Throughout this electric field, our intention is to determine the electric field intensity at a given point for a given charge distribution. Now let us take a case wherein we have got 10-point charges and we are required to find out what is the total electric field. What we can do is, we need to consider each of these point charges. We can consider Q1, find out what is E1. Consider Q2, find out what is E2. Like that, last one, Q10, find out what is E10. So the total electric field intensity is going to be E1 plus E2 plus E3, so on up to E10. So adding 10 vectors is going to be quite difficult. So this way of finding the electric field intensity becomes more and more tedious as the number of point charges increase. What is the other way of finding the electric field intensity? One can apply Gauss law. What is Gauss law? Closed integral d dot ds is equal to charge enclosed. So in order to apply Gauss law, we need to consider a closed surface. That closed surface is known as the Gaussian surface. So because we ourselves define that closed surface, we know what is expansion of ds. And we can also find out how much charge is enclosed. So the only unknown quantity here is d. So once you find d, electric field is equal to d divided by epsilon. So electric field intensity can be obtained. So Gauss law suggests another way of finding out the electric field intensity. But the problem with the Gauss law is, unless the charge and the Gaussian surface are symmetrical, it is not possible to evaluate this integral. It is something like, suppose there is a point charge of q coulombs, and then at the center of imagine a spherical surface with the center of the sphere coinciding with the origin, and where actually I'm placing q coulombs of point charge. Now you can see that you take any point on the spherical surface, the distance is going to be same, which is nothing but radius r. So if you evaluate the electric field intensity, at every point on the spherical surface, electric field is constant, q by 4 pi epsilon naught r square ar. So one can say that the Gaussian surface, the spherical surface here, and the point charge are symmetrical with respect to each other, in the sense that the magnitude of the electric field intensity is going to be constant at every point on the imaginary spherical surface. But once the symmetry is disturbed, suppose if I include another point charge of q1, Gauss law is still applicable. If you evaluate the total flux, leaving out this spherical surface, it becomes q plus q1. Still, this Gauss law is applicable. But once the symmetry is disturbed, symmetry between the charge and the surface that we considered, then evaluation of this integral becomes very, very difficult. So closed integral d dot ds, in this case, now it becomes q plus q1, but evaluation of this closed integral d dot becomes very tedious. So that is a problem with the Gauss law. Now, is there any other way of finding the electric field intensity? Yes, the answer for this is yes. Let us go with the same problem. At point P, instead of finding the electric field intensity directly, is it possible to define a scalar quantity? And from the scalar quantity, can we find out the electric field intensity? Yes, that scalar quantity is the potential function. Afterwards, we are going to see that V is equal to Q by 4 pi epsilon naught into R. In fact, we already derived this expression V is equal to Q by 4 pi epsilon naught into R. So we can see that potential is basically a scalar quantity. So first find out what is V1 at point P because of this Q1. Suppose if the resistance is R1, V1 is equal to Q1 by 4 pi epsilon naught R1. Then find out V2, Q2 divided by 4 pi epsilon naught R2. Like that Q3, when you consider V3 is equal to Q3 by 4 pi epsilon naught R3. Like that, the total potential V is equal to V1 plus V2 so on up to V10. Remember that now each potential E1, V2, V3 so on up to V10 is a scalar quantity. They don't have any directions. It is just like adding the magnitudes 2 plus 30 plus 40 like that. Because they don't have any directions. So adding 10 scalar quantities is much easier compared to adding 10 vector quantities. So once we have this potential function, electric field is given by E is equal to minus of grad V. So we have seen how this potential function has played an important role in the case of electric field, static electric field. So now, having seen number of similarities between the electric and magnetic fields, can we not define a similar function in the case of a magnetic field? So when we have got E is equal to minus grad V, naturally we will be tempted to define a similar quantity in the case of magnetic field. Let that scalar magnetic potential is Vm. Then how to define this Vm? The counterpart of E in the case of magnetic field is H. So let me define H is equal to minus grad Vm. But remember that H is equal to minus grad Vm is not a derived expression. So how to check whether this H is equal to minus grad Vm is acceptable or not? What we can do is we have del cross H is equal to J, which is a derived expression. There is no dispute as far as a curl H is equal to J is concerned. So now H is equal to minus grad Vm. So if I substitute del cross minus grad Vm must be equal to J. But unfortunately, um, curl of gradient of any scalar quantity has to be 0. So on the left hand side, this becomes 0. On the right hand side, it suggests that it must be equal to J. So we can define H is equal to minus grad Vm or the scalar magnetic potential in a region where the current density is 0, conduction current density is 0. So probably in a dielectric material, because we don't come across any conduction current, so in that dielectric material, in that region, one can define this scalar magnetic potential. So with such restriction, we have to define this scalar magnetic potential. So H is equal to minus grad Vm is acceptable, but with the condition that it cannot be defined in a conductive region. Only in a dielectric material where J is expected to be 0, we can define this scalar magnetic potential. Now, is it possible to define any potential function without such restrictions? That magnetic potential is going to be a vector magnetic potential. Okay, let us see how this vector magnetic potential can be defined. See, we have this Maxwell's equation that divergence B is equal to 0. And there is one identity, divergence of curl of a vector is equal to 0. Divergence B is equal to 0. That means B can be written as curl of some vector. So B is equal to mu H is equal to curl A. So A is defined as a vector magnetic potential. So when I substitute this one in curl H is equal to J, curl of H, what is H? 1 by mu curl A is equal to J. So curl A is equal to mu J. What is expansion of curl of a vector? Grad divergence A minus del square A must be equal to mu J. Now what is divergence A? Divergence A is not defined. Only we have defined curl A as P, which is equal to mu H. According to Helmholtz theorem, if you want to define any vector uniquely, both divergence and curl of a vector needs to be defined. So unfortunately here, only curl is defined. Curl of A is equal to B. What about divergence A? We were silent on defining divergence A. Divergence A can be defined as per the requirement. Normally, for static fields, we take divergence as 0 for static field. This is what is known as the Coulomb gauge condition. Similarly, we got a Lorentz gauge condition also. Divergence A is equal to minus mu epsilon dou V by dou T. Anyway, that we are not going to discuss right now. So, because we are restricting ourselves to static fields, for which divergence A can be defined as 0. So, let us go back here. Minus del square A is equal to mu J. So, del square A is equal to minus mu J. And we have got an equivalent expression in the case of electric field. Del square V is equal to minus rho V by epsilon. Del square A is equal to minus mu J. Del square V is equal to minus rho V by epsilon. That is what is known as the Poisson's equation. Now, because this equation del square A is equal to minus mu J is more or less similar to the Poisson's equation, this particular equation is known as Poisson's equation applicable for magnetic field.